Hello, everyone. Welcome back. Mary Mats here. And well, today I'm going to do the NJIT Calculus 112 Common Exam Review, number 3. And, it's only, I think, 9 questions. It's not that long. So it's going to be pretty brief, hopefully. I'm going to go over what's going to be expected on the exam and so on. So if you have some time, I'm going to show you that I'm doing a survey. Okay, I'm going to do a student performance survey for a project. This is for a research project for one of my classes. So please go ahead and fill the survey out. I'll really appreciate it if you did. So just copy this link, okay, and paste it to the just type that link into URL and fill out the survey. All right. So let's see what's going to be expected on this exam. So if we go over here, okay, we can see that the exam is going to cover chapters 10.1, okay, on sequences, up to 10.8, which has Taylor and Maclaurin series. The chapter 10.9, okay, is not going to be included on the exam, which is on convergence of Taylor series, meaning that the remainder estimation theorem will want to be on the exam. So we're going to be expected to find the limit of sequences, some in geometric series, telescoping series, doing the different tests for convergence and divergence, interval of convergence, radius of convergence, finding the first few terms of the Maclaurin-Taylor series, and also our professors have gone a little bit, ahead in the textbook. So we did chapter 10.9, and chapter 10.9 allowed us to memorize some of the important series that we have to know. So they're expecting us to have memorized, the main Maclaurin series, like sine of x, e to the x, cosine x, and so on. So that's important to know. If you know those, you can just write it out, okay, and use it for a substitution problem. So I think it's somewhere over here. Some power series to memorize. So if you know all of this, if you memorize the 6 power series, you'll be fine. Okay, you can write it out, you can use it, so you don't have to start from scratch. Okay, so just keep that in mind. So let's see what we have here. Okay, so this is going to be pretty brief. I'm going to skip one question, actually. I'm going to switch it. I'm going to change it for this. So this was on the remainder estimation theorem. I'm going to replace it for a telescoping series problem. All right, so let's get started. Okay, so for this one problem, we have to find the radius of convergence and the interval of convergence for the power series. Okay, so note that the entire second page for this exam is spaced to finish this problem. So it's that long, okay? Let's get started. So this over here, okay, seems to be just some regular series, okay? It's a power series, and we want to test the convergence of the series. Usually, we would use either the root test or the ratio test, but that depends on how the limit is evaluated, right? How easy it is to evaluate the limit, okay? In this case, I believe that the ratio test is easier to evaluate, okay, just because you don't want to find the nth root of a root, right? You will have to find the nth root of a radical, and that's just not, it's not nice. So you want to avoid, getting complicated limits for no reason. So that's why we will do the ratio test. So let's do the ratio test. Okay, so for the ratio test, we have to have, okay, an absolute value of our a sub n. So whatever is inside the series, which is the sequence, will be a sub n, and we want to find the absolute value of a sub n. the absolute value of a sub n is the absolute value of x to the power of n divided by 3 to the n times the square root of n squared plus 100. Okay, so that will be a sub n. And the ratio test states that if we want to test for convergence, we want to take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Okay? So we know what a sub n in absolute value is. We can find a sub n plus 1 and then find the ratio between them. So let me go over here, since we're going to need a lot of space to prove that this converges. You know, it's obvious that it's going to converge because the question explicitly asks for the radius of convergence. So you already have an idea of the convergence. Now, over here we're going to have the limit, okay, as n approaches infinity of the absolute value of a sub n, right? So that's going to be x, an absolute value, to the power of n plus 1. We have to add 1, right, to each n. All of that's going to be divided by 3 to the power of n plus 1 times the square root of n plus 1 squared plus 100. All right, so far so good. And then we're going to divide by the reciprocal, okay? Well, we're going to multiply by the reciprocal of a sub n, which is essentially just divided by, okay, a sub n. So if we divide by, okay, the absolute value of x to the power of n divided by 3 to the n times the square root of n squared plus 100, it's essentially multiplying by the reciprocal of it. So we have the limit as n approaches infinity of the absolute value of x to the power of n plus 1 divided by 3 to the power of n plus 1 times the square root of n plus 1 squared plus 100. All of this multiplied by the reciprocal, which is 3 to the n times the square root of n squared plus 100 divided by the absolute value of x to the power of n. All right, so here we can do some really nice simplifications, so we can use the power properties for these ratios. So if we have the absolute value of x to the power of n plus 1 divided by the absolute value of x to the power of n, we can subtract its powers. So we're going to have n plus 1 minus n, which is just 1. So we have the limit as n approaches infinity of the absolute value of x. Okay? Now, what else can we simplify? This over here is 3 to the n, and here we have 3 to the n plus 1. We can split off a factor, okay, of 3 to the n plus 1. 3 to the first power. But we could, you know, simply subtract the powers, and we're going to get that n minus 1 is going to be negative 1. 3 to the negative first power is 1 over 3. So that 3 goes down. And then we're going to have the square root of, okay, all of that, n squared plus 100 divided by n plus 1 squared plus 100. Okay? Look at that. It's looking nicer. I mean, it's still not nice enough, but we can make it look nice. So let me take out the absolute value of x over 3 out of the limit, since it's a constant. So we have the absolute value of x divided by 3 times the limit, okay, as n approaches infinity of the square root of this crazy expression, n squared plus 100 divided by n plus 1 squared plus 100. Okay, so here what we will do is not use L'Hopital, right? L'Hopital is not appropriate in this case because it's just too much, right? I mean, you're going to get infinity over infinity, but you're not going to do L'Hopital. You're going to be smarter. You're going to divide, okay, the inside of the radical. You're going to divide by, okay, n. You're going to divide by n squared on top and bottom. That 2 doesn't look like a 2. There you go. So we have absolute value of x divided by 3, okay, times the limit as n approaches infinity of the square root of, right, n squared over n squared is 1, and then we have plus 100, over n squared divided by the n squared, okay, plus 1, n plus 1 squared, okay, and then divided by n squared. We can bring that n inside of the squared, so we have n plus 1 divided by n, all of this squared, okay, plus 100 over n squared. And we already know that the limit, okay, of n plus 1 divided by 1 as it approaches infinity, as n approaches infinity, will be 1, right? We could do the same process. If you want to show all the work, you know, then you will have to rewrite this. You will have to rewrite this as x in absolute value divided by 3 times the limit as n approaches infinity of the square root of 1 plus 100 divided by n squared divided by 1 plus 1 over n. I mean, I don't know if professors will be mad, okay, if you just say that this goes to 1, right? If this goes to 1. I mean, I don't think that will be an issue. But, you know, just to be safe, you could just show this extra step. So this is 1 plus 1 over n, okay, over 1 squared. And then when you take the limit of that, all of that's going to go to 1 times the constant, which is the absolute value of x over 3. So that's going to be the limit. And we know that for values of x in absolute value divided by 3 that are less than 1, then the series will absolutely converge, right? So this will converge, right? Converges for those values of x, right? When x absolute value over 3 is less than 1. And we can already say that the radius of convergence will be 3. If we multiply by 3 on both sides, we get that the absolute value of x is less than 3. So the radius of convergence is 3. Okay, now we can solve the absolute value, and then we get that x is less than 3 and greater than negative 3. But this is for absolute convergence, right? We need to test each of the endpoints to see if it converges conditionally, right? So we'll need to still analyze both of the endpoints and see what happens. So let's analyze, okay, the endpoint at x equal negative 3. So at x equals to negative 3, then we have the sum, okay, from n equals 0 to infinity of, okay, x to the power of n, right? So if we substitute x by negative 3, we have negative 3 to the power of n divided by 3 to the power of n times 1 over the square root of n squared plus 100. This over here will go to negative 1 to the n, right? So that means we have a alternating series. Okay, so that's just going to be the sum from n equals 0 to infinity, negative 1 to the n, divided by the square root of n squared plus 100. Oh boy, I don't have space. Okay, so that's just... Okay, there we go. So this over here converges by the AST, or the alternating series test. Why? Well, all conditions of the alternating series test are met, meaning that the first condition, where u sub n is this expression over here, which is the sequence without the alternator, negative 1 to the n, is going to be positive, okay, for all values greater than or equal to 0, the index. Second, it's a non-increasing function, right? That means that u sub n is greater than u sub n plus 1. All right. Now the third condition is that the limit of u sub n goes to 0. So essentially, u sub n will go to 0 when you take the limit of 1 over the root n squared plus 100 as n goes to infinity, it goes to 0. So converges by AST, meaning that the endpoint at x equals negative 3 is inclusive. Now let's analyze the last one. So at x equals to 3, we have the sum, okay, from 0 to infinity of 3, okay, over 3 to the power of n, that's just 1. 1 to the n is 1, right? And then times 1 over the square root of n squared plus 100. This over here, okay, we can do a comparison test. We can do a comparison test or a limit comparison test if you wish. So if you want to do a limit comparison test, okay, you could say that your a sub n, okay, a sub n is equal to 1 over the square root of n squared plus 100. And you want to compare that to something that doesn't have this 100, right? So that this whole fraction will be greater, right? Because the denominator is being made smaller. So b sub n will be, okay, 1 over the square root of n squared. And we know that this is 1 over n, right? Which is, if we find the sum of bn diverges, okay? We know that diverges because it's a harmonic series. Okay, it's a harmonic series. All right, so that's important to note for now. But now we have to take the limit. We gotta use the limit comparison test. So the limit as n goes to infinity of a sub n over b sub n equals to 1 over the square root of n squared plus 100, and then divided by 1 over the square root of n squared, which is multiplied by square root of n squared. We can bring that inside of the limit. Okay, we can bring it inside of the limit, and we get that the limit is 1. Okay, 1, which is some value c less than 0, meaning that by part 1 of the limit comparison test, both the sums of an, okay, and the sum of bn either converge or diverge. So we're going to use the fact that we know the convergence of the sum bn, right? The sum of bn. We know it diverges. So if Vn diverges, the sum of Vn diverges, then the sum of An diverges as well. So this endpoint, okay, at x equals 3 is not included. And finally, we can conclude, okay, that the ratio, the radius of convergence, I misspelled that. The radius of convergence is 3. And the interval, okay, the interval of convergence is going to be, okay, closed, right, closed bracket from -3 to 3 and then parentheses. That will be your interval of convergence. Okay, and you want to mention that it was by the limit comparison test, right? So this was, yeah, you should not forget that. So just write everything out. So sum of An diverges by LCT. And then you get your full points. Okay, this was a pretty long problem, honestly. I don't think that there will be something like that. Hey, Nick, what's up? He asked if you can do another 111 one that will be sick. Okay. Yeah, actually, one of my friends suggested me to do a problem from the 2018 review because apparently it's a little hard. It's going to be question 5, I think. Yeah, question 5 is on optimization. I'll do that later. Okay. So yeah, I'll be willing to do it. Why not? Okay. So this problem was a little long. I don't know why. I mean, all of this is required to prove that this series converges, right? And then that it conditionally converges at these points, at only one point, and we found the interval of convergence and the radius of convergence. So that's it for this problem. I mean, that's the reason for why they gave you like 2 pages for that. See, the next page is just for that. Continue problem number 1 from previous page. And over here, they have this curious thing over here. They have, okay, the quality of notation, logic, organization, and or neatness of this page is circle 1. It seems like a grading rubric. Okay, so it depends on like how well you answer to the prompt, how logic your work is, how logical. All right, so now for question 2, which is a lot shorter than question 1. Okay, we're going to determine if the following series converges or diverges. If they converge, okay, find their sum and clearly show all your work, including any applicable tests for convergence. So for this sum over here, let's see, we have the sum from n equals 0, okay, to infinity of -1 to the n divided by 2 to the n plus 1, 2 to the 2n plus 1, okay, and we want to see, okay, if they converge, if it converges or it diverges. So we can do some manipulation in here. We can rewrite this as the sum, okay, from 0 to infinity of -1 to the n divided by 2 squared, okay, 2 squared to the n, and then we can split off a factor of 2 to the first power, so times 2, okay? So look at that. That's very familiar, right? That looks like a geometric series, and essentially that's what it is. It's a geometric series, so that's going to be the sum, okay, from 0 to infinity of -1 to the power of n divided by 4, right, to the n, okay, and then times 1/2. So this is a geometric series, okay? So it's a geometric series with r in absolute value is less than 1, right? And in this case, r is equal to -1/4, and a is equal to 1/2. So this converges, okay, the sum converges to, okay, a divided by 1 minus r, which is 1/2, okay, divided by 1 minus 1/4. That's going to be 1/2 divided by 1 plus 1/4. We multiply by 4 on top and bottom, and we get that Sn is equal to 2 divided by 4 plus 1, which is 5, 2/5. All right. Now, for part B, okay, we have the sum of 1 over 10 plus e to the 2 over n, okay, and this one, I forgot to mention that you should be able to, recognize whether the sequence, okay, of inside of a sum diverges or converges, like if it approaches 0. So usually you should be able to do the nth term test in every problem. So like you should be able to just do it in your head, like, okay, just see where the limit as it goes to infinity is. If it's other than 0, then you know it's going to diverge. So the nth term test is actually very useful. And here's where we're going to use it. Because what happens when we take the limit of the sequence as it goes to infinity? So the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 1 over 10 plus e to the second power over n. Okay, so when n goes to infinity, this expression over here, okay, goes to 0, right? E to the 0 is 1. So it goes to 1 over 11. And 1 over 11 is essentially greater than 0. So the series diverges by the nth term test. Okay, the nth term test for divergence. All right, for problem 3, determine if the series converges conditionally, converges absolutely, or diverges. Clearly show all work, including any applicable tests for convergence. Okay, so for this one, it looks like we can find the absolute convergence since it's an alternating series. We can already kind of see that it's, decreasing for all the values of x. Hey, how are you? So we're going to find a sub n in absolute value. Okay, that's going to be simply 1 over 2 n plus 3. So we want to use a test for divergence, or we don't even have to, okay, use the ratio or root test, because this is a pretty simple sequence, right? So we find the limit as it goes to infinity, it goes to 0. So nth terms test for divergence does not work, it fails. But one thing we can do is we can use one of the comparison tests, right? We can use the limit comparison test. So how about we use the limit comparison test? So we can say that, okay, we can say that our Vn that we're trying to compare to An is going to be 1 over n, right? Because over here we have simply a first power on the bottom, first power of n. So we know that a sub n in absolute value is greater than 0 and b sub n is greater than 0, okay, for all n, okay, is greater than or equal to 1. That works. So the limit comparison test can be applied. And so we're going to go ahead and take the limit as n goes to infinity. Okay, the limit as it goes to infinity of a sub n divided by b sub n. And that's just going to be, in absolute value, yeah. So that's going to be n divided by 2n plus 3, right? Because 1 over n divided by, 1 over 2n plus 3 divided by 1 over n is just that the reciprocal of this times this, right? This over here. So it's just that. And the limit as this goes to infinity, well, we divide by n on both sides, okay? We divide by n, and don't forget to put your limit in there. That's going to be the limit as n goes to infinity of 1 over 2 plus 3 to the n, 3 over n. This goes to 0, so the limit goes to 1/2, which is some value c, okay? Some value c that is greater than 0. Right, according to the limit comparison test. So, okay, if it's greater than 0, we know that either both series, okay, both series of a sub n, okay, and the sum of b sub n both converge or both diverge, right? We know the divergence or convergence of b sub n, right? The sum of b sub n. It's a harmonic series. So the sum of b sub n diverges because it is a harmonic series. Okay, so that means that therefore the sum of a sub n diverges. Okay, the sum of the absolute value, don't forget, diverges. So that means it does not converge, okay, absolutely, but it could certainly converge conditionally because it's an alternating series. And as we can see, if u sub n, okay, is equal to 1 over 2n plus 3, u sub n, okay, is always positive. Okay, so u sub n, so the first condition is that it's always positive. The second condition is that u sub n is always greater than u sub n plus 1, or eventually non-increasing. That's true. It's an always decreasing function. And the third condition is that u sub n approaches 0. All of these conditions are met. Okay, so that means that this converges, okay, by the alternating series test. It converges, okay, and it's simply, okay, you could say, okay, already that because it does not converge absolutely, it converges conditionally. So converges conditionally. And then by the AST, alternating series test. Okay. All right, so let's see. For question 4, suppose that the series, okay, the sum of, okay, from n equals 0 to infinity of -1 to the n times f of n is shown to be convergent by a ratio test. Remember that the ratio test, okay, is simply the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. Okay, and then we know that if this limit, okay, if this limit equals to some value rho that is less than 1, it will converge absolutely. Okay, so let's see. It's shown that this is convergent by ratio test. Is the series the sum, okay, the series of f of n, right, as from n equals 0 to infinity, convergent, divergent, or is it unable to determine? Carefully explain how you know or what necessary information you're missing. All right, so for this one, we could simply use the ratio test using what we know, which is our a sub n, right? So if a sub n equals to -1 to the nth times f of n, then we know that the absolute value of a sub n will just be f of n in absolute value, right? Because the alternator will just be always positive. It's an absolute value. Okay, so we can take the limit as n goes to infinity of the absolute value of a sub n plus 1. So that's going to be f of n plus 1, and then divided by a sub n, which is going to be f of n, will be equal to some value rho. And because we're told that this is shown to be convergent by the ratio test, then that value rho must be less than 1, which means that it converges absolutely. Okay, it converges absolutely. And so this over here, okay, it converges. It simply, okay, converges absolutely. So the sum of -1 to the n times f of n from n equals 0 to infinity converges absolutely, okay? But what is the question? The question is asking, okay, carefully explain how you know, okay, so yeah, so it's asking, is the series, that is, okay, the absolute value of the series convergent, divergent, or is it unable to determine? Okay, well, we know that the series over here, this one, converges absolutely. And that's because the series of this converges, right? We know that that converges because it's basically, we're taking the limit of the absolute value of this over here, which is -1 to the n times f of n. And that's basically the, okay, series over here, f sub n. So if that converges absolutely, okay, the original series converges absolutely, then, okay, the series from n equals 0 to infinity of a sub n converges. That's all. You don't have to say it converges absolutely because that will be redundant and you're going to get points off for that. Because it's just, you know, it doesn't make sense to say, okay, something converges absolutely, even though it's always positive, right? So it just converges. That's all. Next question. So for question 5, we're going to find the Taylor polynomial P3 of x that uses a Taylor series centered around x equals pi over 4 to approximate f of x equals sine x. Okay, now for this question, we know that the series, okay, the Taylor series around some point A, right? So the Taylor series is going to be the sum from n equals 0 to infinity of the f, okay, to the kth derivative of the value a times x minus a to the power of k divided by k factorial. Okay, so that's going to be the definition of the Taylor series around some point A, okay? And we want to approximate the Taylor series around this point for sine of x. Okay, so first things first, and we will just find the Taylor polynomial for the first 3 terms. So that's what we're trying to look for, right? The first three k, right? So that's going to be, we need to find the values of the derivatives, right? So we need to find f of 0, f to the 0th derivative at a, which is essentially just a function, right? So we need to find f of a, okay? We need to find f prime of a, we need to find f double prime of a, and f triple prime of a, okay? And we know that a is equal to pi over 4, okay? So if a is equal to pi over 4, then f of a is sine of pi over 4, which is root 2 over 2. Now, for f prime of a, the derivative of sine of x is cosine x. So cosine of pi over 4 is the same, is root 2 over 2. Now, f double prime of a, that will be negative sine of x, so negative sine of pi over 4 is negative root 2 over 2. And the same negative cosine of pi over 4, okay, the derivative of negative sine is negative cosine, and you get negative root 2 over 2. All right, we found all the needed derivatives, okay, and the needed value of the function at a. Now, what else do we need to know? Well, usually it would be nice to simply start writing out, okay, the terms, the first terms. So we're going to find the sum, okay, from n equals 0 to 3 of, okay, the values for f, okay, of k. Actually, I'm doing something wrong here, if you notice. This should be consistent with the index, right? So if I'm writing index as n, this should be n as well. Okay, so just, we gotta be careful with that. All right, so the nth derivative at, okay, pi over 4 times x minus pi over 4 to the n divided by n factorial. So we're gonna write out this sum over here. So that's going to be simply the Taylor polynomial for the 3 terms. Well, we don't know if it's gonna be 3, it could be 4. And I can see that it's gonna be 4 now. So that's going to be f, okay, to the 0th derivative, that's just f of x, right, at pi over 4, so that's root 2 over 2. Now we're going to do plus, okay, the first derivative at pi over 4, which we found to be root 2 over 2 again. Now we're going to multiply by x minus pi over 4 to the first power, right, because now it's n equals 1. Here this is n equals 0. This is n equals 1. Now we're going to do the next one. We're going to do n equals 2. And we found that the derivative at the second derivative was negative root 2 over 2. And then that's going to be times x minus pi over 4 to the second power. And now we have over 2 factorial. And the last one is going to be, let me move this over here. There you go. Okay, the last one is going to be negative root 2 over 2 times x minus pi over 4 to the third power over 3 factorial. Those are, okay, the terms for this Taylor polynomial. And you can simplify it if you want. Okay, so if you want to simplify it, you're going to get that this is, okay, equal to the Taylor polynomial for n equals 3 equals to root 2 over 2. Okay, and I think I don't know if it would be okay to factor it, to factor the root 2. I mean, I would just leave it there. It doesn't matter. It's the same thing. So root 2 over 2 plus root 2, okay, times x minus pi over 4 divided by 2 minus root 2 times x minus pi over 4 squared divided by 2 times 2 is 4. Okay, so that's going to be the third term. And then we're going to do the last one. So minus root 2 times x minus pi over 4 to the third power divided by 3 factorial times 2, which is basically 6 times 2, which is 12. And that's going to be the Taylor polynomial at n equals 3. All right, so now the next question was about the remainder estimation theorem. But as we know, the remainder estimation theorem won't be on the exam, so I have replaced that by a telescoping series, because telescoping series will be on the exam. So let's just review a simple example of a telescoping series. So we find that this telescoping series, okay, is just, you know, the sum from 1 to infinity of n squared, 1 over n squared plus n, and we want to find the sum of the telescoping series. When they say to find, okay, the sum of the series, that means that the sum has to converge, right? There has to be no way that it will diverge if they already, you know, are saying that there's a sum and that, you know, they're asking to find the sum. So it's nice to know that it will converge. So let's see. This sum can be rewritten as, okay, sigma of 1 over n squared plus n, which is sigma of 1 over n times n plus 1. So I'm factoring out the bottom, the denominator. And if you're wondering, why am I not writing n equals 1 to infinity over here and over here? Well, simply because this is standard notation. If you have the sum from 1 to infinity, it is implied, okay, that sigma will be the same. It's just standard mathematical notation. So let's do, okay, in order to find a telescoping series sum, we need to find the terms, right? We actually have to write out the first few terms to see what's the pattern and to see if something will cancel out. Okay, so, but to do that, we have to kind of split this fraction into a sum of partial fractions. So that's why you heard we're going to do a partial fraction decomposition. So the partial fraction decomposition for 1 over n times n plus 1 will be some value a divided by n plus some value b divided by n plus 1. Now we find the least common denominator, and we get that 1 over n times n plus 1 is equal to a times n plus 1 plus b times n. Okay, all of that times n divided by n times n plus 1. This cancels out, and so we get that 1 is equal to a times n plus 1 plus b times n. Okay, and you could do two ways. You could solve this in two ways. You could either do the classical way of solving this, and so by factoring out the values of a and b with respect to each power of n. So we can say that this is a plus b times n, and then plus a, right? And then you can say that because on this side of the equation there is only a 0th power, then the 0th power of this side of the equation will be equivalent. So a equals 1, and then the first power will be equal to 0, the coefficient of the first power. Okay, so if a equals 1, then therefore b equals negative 1. The other way, which is a little bit, kind of shunned away by mathematicians, just because it's a shortcut, right? It's just by letting, okay, let n equals to 0, for example, so that this term over here will cancel out. Then we get that 1 equals to, okay, a, that quickly. We can also find some value so that this over here is 0. So we can let n equals to negative 1, and we get that negative 1 plus 1 is 0, so we have 1 equals to 0 plus negative 1 times b. So b equals negative 1. And I think this is faster than that. I don't know if professors will be concerned if they find that you're using this method, but I think it's valid. Okay, so I don't know if they're gonna take my song for that. I mean, I'll do the classical way if it's a simple problem. I'll just do the classic way because it's just to be safe, right? Okay. Now then, let's go to the next problem. Find the full Taylor series representation of f of x equals 1 over x squared centered around x equals 3. Okay, so for this one we do the same, okay, the same drill. We have to know that the series, okay, is going to be 1 over x squared. So the function is 1 over x squared, and we can represent it as the sum from n equals 0 to infinity of the nth derivative of 3, because we're centering it at 3, times x minus 3 to the power of n divided by n factorial. Okay, so usually what we do is, of course, find the first derivatives to see what's going to be the pattern, right? So let's find the first few derivatives. So the zeroth derivative is just the function. So f of 3 is just 1 over 3 squared, right? F prime of 3, okay, f prime of x is going to be negative 2 over x cubed, and therefore f prime of 3 is equal to negative 2 over 3 cubed. So we're starting to see a pattern. We see that the denominators have 3 to some power, some increasing power. Okay, so let's see what's going to be the second derivative of x. of f of x, that's going to be negative 2 times 3 times negative 3, right? So that's going to be positive, divided by x to the power of 4. And notice that I'm not, simplifying the numerator because of, a simple reason that the derivatives, okay, every time you take a derivative, the numerator will be multiplied by an increasing number, meaning that it sounds like a factorial, right? So it sounds like n factorial. So I'm just going to leave it like that. And therefore, f double prime of 3 is equal to, 2 times 3 times 1 divided by 3 to the power of 4. And I think that's enough to see the pattern over here, okay? We see that on the numerator we have n factorial, okay? We have, so the nth derivative of 3 is going to be n factorial, right? And then we also see that for each derivative we have an alternation of sign. First derivative, the 0th derivative was positive, first was negative, third was positive, and so on. So that means we're multiplying by a alternator, which is negative 1 to the power of n, starting at 0, right? Because negative 1 to the 0 is 1, so that works. And also the bottom, okay, we'll start to see, okay, you will start to see that this is going to be 3 to some power, right? But now at 0, it starts at 2. So you want to start with n plus 2, because at n equals 0, it's going to be 3 squared. Okay, so that's looking good for now. Let's see. So what else is here? So let's see. What can we draw from this? So what's happening is that over here, we have a n factorial over here. But where is it starting? That's the question. So we have to be careful here, because we have to check that this is right, that this is the right n factorial. So at the 0th derivative, okay, 0 factorial is 1, that works. Now over here, okay, 1 factorial doesn't seem to be right? Because 1 factorial is 1, but it starts at 2. So we have to adjust that. Okay, to instead n plus 1, because at 1 it will be 1 plus 1, 2 factorial, and that works. So n plus 1 factorial, okay? So that's going to be our derivative term. So we can say that the Taylor series representation as a sum, right? As a sum will be something like this. So we can say that f of x is going to be the sum, okay, from n equals 0 to infinity of this over here, right, which is the nth derivative at 3, and that we found to be n plus 1 factorial times negative 1 to the n divided by 3 to the power of n plus 2, and then multiply by, on the bottom, n factorial, right, from this over here, and then on the top we have x minus 3 to the power of n. All right, that's looking good. So this is essentially, okay, the answer. We can simplify this further by saying that f of x, okay, f of x is equal to the sum from n equals 0 to infinity of n plus 1 factorial over n factorial is going to be n plus 1, and then that's going to be multiplied by negative 1 to the n times x minus 3 to the n divided by 3 to the n plus 2. And I believe you can write this as your answer, okay? This is valid, although they are not asking for the sigma notation. So suppose that, you're having trouble finding the sigma notation. You could just write out, okay? You could just write out the first few terms, right? But I think the sigma notation is just a nice way to do it. It's just so nice. Look at that. It's one single expression. But let's say that you're having trouble finding the pattern. You could write out the first few terms. So suppose that we're going to write out the first few terms. So for the first few terms, we have that the first derivative, right? The first derivative was, the zeroth derivative was 1 over x squared, so that's going to be 3. So we start with n equals 0, right? So that's going to be 1 over 3 squared. Now the second derivative, the first derivative will be negative, so minus 2 over 3 to the power of 3, right? And we have to multiply it by, x minus 3 to the power of 1. And we keep on doing that, right? So that's going to be plus, the next term will be plus 3 times 2 is 6. So we have, or we could say 2 and then times 3 to the first over 3 to the fourth. That will simplify as 1 over 3 to the third times x minus 3 squared over 2 factorial. And then minus that, right, to infinity. Okay. And I think it's still valid if you just say that this is 1 over 9 minus 2 over 27 times x minus 3. And then plus, this 3 cancels out with 1 power. So that's going to be plus. And the 2 cancels out, right? 2 over 2 is 1. So that's going to be x minus 3 squared divided by 3 to the power of 3, which is, 27. And then minus the rest of the infinite terms. And this can also be a valid answer. This can also be a valid answer. But don't forget to write the 3 dots at the end, or you're going to have some issues. So either of them are correct answers. So let's move on to the next problem. For problem 7, we have to find a Maclaurin series for the function f of x equals x sine 3x. Now, hint, the substitution method using a well-known Maclaurin series will be the quickest. Write your answer using summation notation. In this case, it's required of us to write a summation at the end. So that's important to keep in mind. Also, they're asking for the Maclaurin series. That means it's the Taylor series centered at x equals 0. So that means it's going to be easy. So if we know our Maclaurin series, right? You know that the Maclaurin series expansion for sine of x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus, x to the n, 2n plus 2 plus 1 divided by 2n plus 1 factorial. So that's the Maclaurin series for sine of x. So if we use a substitution method, which is essentially just substituting, right, like plugging in the value for sine of x, then we can find this series easily. So we know that this is expressed as the sum, right, because we wanna write it as a summation. So this is the sum from n equals 0 to infinity of, x to the power of 2n plus 1 divided by 2n plus 1 factorial. This is one of those that you have to memorize. It would be nice to know, right? You don't want to derive the Maclaurin series of sine of x from scratch. That takes too long. Not that long, but it just saves some time, right? So just make sure you memorize it. It's not too hard to memorize. So we're going to use the substitution method, and we have that our function f of x, right? So f of x is equal to x sine of 3x. And so the substitution that we have to make for the quickest, way to solve this is just 3x, right? We substitute 3x into our summation. So basically, f of x is equal to x times the sum from n equals 0 to infinity of 3x to the power of 2n plus 1 divided by 2n plus 1 factorial. We can bring the x inside, this x over here, we can bring it inside and then simplify it. So this is essentially the sum, from n equals 0 to infinity of 3 to the power of 2n plus 1, and then times x to the power of 2n plus 2 divided by 2n plus 1 factorial. And this over here will be the series expansion for x sine of 3x. All right, we're gonna use that. Oh, and also don't forget that we have to consider the alternator. So yeah, my bad. This over here is actually times negative 1. Yeah, because we have an alternation of signs. Okay, so this over here has to be included. All right, so this will be the series representation for x sine of 3x. Okay, don't forget the alternators. Okay, very important. See, I almost forgot it right there. So don't forget that the signs are extremely important. So see if there's a change in sign. All right, let's see. So for part B, use the ratio test to find the radius of convergence of the interval and the interval of convergence for the above series. All right, so let's see. All we have to do is use the ratio test. So that's going to be an easy way to find it. So for part B, okay, we're going to have to find, okay, the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, right? And so we have to state that a sub n is going to be, in this case, 3 to the n plus 1, 3 to the 2n plus 1, excuse me, times x to the power of 2n plus 2. Okay, an absolute value, right? Because this is the absolute value of a sub n. And then times the alternator, negative 1 to the n, divided by 2n plus 1 factorial. Okay, so now we can go ahead and evaluate the limit of the ratio test. So this is going to be the limit as n goes to infinity of a sub n plus 1, which will be 3 to the power of 2n plus 2, because when you input n plus 1 into this over here, that's going to yield 2n plus 1, and plus 1 is 2, right? So that's going to be 2n plus 2. Okay, that's going to be multiplied by the alternator, negative 1 to the n plus 1, and then times x to the 2n plus 3, right? Because you're just adding n plus 1. Okay, so all of that is going to be divided by 2n plus 2 factorial. Good. Now we're going to divide by a sub n, which means that we're going to multiply by the reciprocal of a sub n, which is basically 2n plus 1 factorial, divided by the alternator, negative 1 to the power of n, times 3 to the 2n plus 1, times the absolute value of x to the power of n plus 2. Okay, now let's simplify this a little further. Okay, so over here we're going to have the limit as n goes to infinity of, okay, so this over here, 3 to the n plus 2 to the 2n plus 2 divided by 3 to the 2n plus 1 is going to give you a value, okay, and that value will be 2n plus 2 minus 2n plus 1 as a power. And that's basically, okay, 2n minus 2n is 0, and 2 minus 1 is 1, so that's going to be 3. Okay, and then the alternator over here is going to be negative 1 to the power of n. Right, so because n plus 1 minus n, okay, I think, is the alternator going to be included? Well, we're taking the absolute value of this, so really it will always be positive. So we should not include the alternator in the absolute value of a sub n. So this should not go in there, okay, because it's always positive. So that's important to keep in mind. The alternator is going to be out of the expression. So we have this over here a little bit more simplified, right? So x in absolute value to the power of 2n plus 3 divided by x to the power of 2n plus 2 will yield the absolute value of x by using the properties of powers. Now, 2n plus 1 factorial, we're going to leave it as it is on the top. And then we're going to simplify 2n plus 2 factorial, which is going to be 2n plus 2 multiplied by 2n plus 1 factorial. This will cancel out, okay? And we're left with 3, okay? We're left with 3 times the absolute value of x, okay? And then divided by 2n plus 2. Okay, we're going to take the limit as n goes to infinity. Nice. So, we're going to find that the limit as this goes to infinity approaches 0. Okay, this simply goes to 0. And what happens when this goes to 0? Well, according to the ratio test, if this is less than 1, okay, that means that this a sub n, right, this a sub n will converge, okay, absolutely for any values of x. That means that the radius of convergence, okay, the radius of convergence is infinity. Okay, it is infinity. And therefore, the interval of convergence is going to be equal to, in negative infinity to positive infinity. Okay, so this is going to be the answer to the prompt. So that's the interval of convergence and the radius of convergence. Okay, it's always good to double check your work to see if you made any mistakes. Okay, so let's see. I think this should be over here. If you see, okay, if you caught it over here, 3 to the power of 2n plus 1. Okay, 3 to the power of 2n plus 1 is a sub n, right? It's part of a sub n. But what happens when you add 1, okay? When you add 1 to n, okay, that's going to be n plus 1, right? So that's going to be 3 to the power of 2 times n plus 1 to find, okay, the values for a sub n plus 1 over here. So this over here, okay, is actually off by 1 because look at this. This will simplify as 3 to the power of 2n plus 2 plus 1, which is 3 to the 2n plus 3. Okay, so that's my mistake over there. So this will be in fact 3 to the power of 2n plus 3. Okay, so eventually that's just going to simplify. Hey James, as that's going to, yeah, I'm almost done. So this will simplify as 3 squared. Okay, 3 squared times the absolute value of x divided by 2n plus 1 plus 2, and that goes to 0. And because it's less than 1, okay, it's irrelevant, but that could cost you some points. So that's infinity. The radius is infinity, and the interval of convergence is from negative infinity to positive infinity. Okay, so the next questions. For question 8, okay, we're going to determine if the following series converges or diverges, and clearly show all work, including any applicable tests for convergence. Now, this is a very nice problem. So actually, first, what I did was I tried the limit comparison test, and it just went terribly, right? Because it's just a mess. It didn't work. The limit comparison test failed. So usually, for this type of problems, you want to see if it's alternating, okay? Is it an alternating series? Well, if you see cosine square of n, okay, it's going to be positive for all values. So all of these expressions is going to be positive. So that means that, okay, we don't have to worry about the alternating series test, right? Okay, so now we have this over here, and we want to find some test. We want to use a test to find if it converges or diverges. Which test is more appropriate? The limit comparison test fails, so don't even try it. For this type of problems, which is a little bit more complicated, usually when it's oscillating, okay, between two values. In this case, it is oscillating between two values, right? Cosine squared of n plus 2. If you think about it, what is the maximum value of cosine squared of n? Well, the maximum value, okay, of cosine of n will be between, okay, this is going to be between 1, right? Because the maximum value is at cosine of 0, right? Which is 1. And the minimum value will be at pi, is -1. Okay? So what happens when we squared cosine of n? So if we squared cosine of n, okay, it will be different. It will always be between two different values. Okay, so it will be, but remember that over here we have from 0 to infinity, from 1 to infinity, right? So at some point, okay, cosine of, so let's test some values. Cosine of pi, right, or cosine of 0, and then if we square that, that will just be 1. What happens when we take cosine of pi? Okay, cosine of pi is -1. Okay, so that will just be 1 once again, right? But what happens if we take cosine of, okay, cosine of pi over 2? We can dismiss that. That's going to be 0. So if we look at the unit circle over here, okay, so the values of cosine square of n will oscillate, okay, between 0, okay, it will be between 0, but this is going to be 1. So this is 1 0. This is 1 0, right? And over here we have 0 1. Okay, -1 and 0. So the values for cosine, okay, square of n will oscillate between this over here, between 1 and 0. So it will go from here to here and so on, because, you know, the absolute value of that is just going to be from 0 to 1. So once we realize that it's oscillating between 0 and 1, then we can say that cosine of, okay, cosine of n squared plus 2 will oscillate between, okay, 3, right? Because suppose that the maximum value for this will be 1, so 1 plus 2 is 3, and then the minimum value is 0, so it will be between 2 and 3. Okay, so we can use that to find, okay, a comparison. So we can compare this, and then we can divide by whatever value we have for our sequence, which will be the square root of n cubed. So we divided on all sides of the inequality the square root of n cubed. Okay, so for that case, we know that, okay, the convergence of each of them is going to be okay, a convergence, right? So over here, this will converge. The sum of 3 over the square root of n cubed will converge, and the sum of 2 over the square root of n cubed will also converge, okay, by the comparison test. If you think about it, there are p series with p less than 1. So we have to state that. Okay, the sum of 3 over the square root of n cubed converges by p series, right? By p series with p is greater than 1, actually. Yeah, greater than 1. Okay, when p is greater than 1, it will converge. So what's happening here is that we can use the comparison test. So the comparison test says that if the smaller series, okay, if the smaller series will converge, okay, if the smaller series diverges, then the larger series diverges. And then this over here is going to be the smaller series, right? This is going to be the smaller series, and this will be the larger series. And then we're trying to find the convergence of the middle series. So if the larger series, okay, converges, so if the sum of 3 over the square root of n cubed converges, which we know it does, then the smaller series has to converge, right? But then in the other case, if the smaller series diverges, so if this over here diverges, which it doesn't, right, then whatever is larger has to diverge. But we know that that does not apply. So that part of the comparison test will not apply, so we have to use the larger series. So we know that, therefore, the sum, okay, from n equals 1 to infinity of cosine squared of n over the square root of n cubed converges by the comparison test. All right, so now the last problem. For the last problem, okay, which is actually, it was a little tricky when I first did it, but it's actually simple. So let's take a look at it. We're going to find the Maclaurin series representation for the function f of x equals to x minus 1 over k factorial times x to the k, where k is an unknown positive integer. Show all calculations or explain the reasoning for your answer. So to find the Maclaurin series, okay, we know that for the expansion of f of x, we have, okay, the sum from k equals 0 to infinity of the kth derivative, right, of f at 0 times x to the k divided by k factorial. This is our Maclaurin series, right? So let's see if we can find the first derivatives of this polynomial, okay? Because we're trying to find the representation for a polynomial, which is, not very usual. We haven't done this very often, but you will see that it's not too complicated. So if f of x equals, if f of x equals x minus 1 over k factorial times x to the k, and then we take the derivatives, right, at 0. So let's find the first derivative. So the first derivative at 0 will just be, 1 minus 1 over k factorial times 0, right, to the k minus 1, and then times k minus 1. That just goes to 1. We know that f of 0, right, f of 0 will just be 0. If you plug in 0, that will just give you 0. F double prime of 0 will be, if you take the derivative, you're going to get negative 1, times k minus 1 times k minus 2, and then times 0 to the power of k minus 2 divided by k factorial, which will be 0. And then if you keep taking derivatives, right, if you keep taking derivatives, if you take an infinite amount of derivatives, so you keep doing this, to the up to the kth derivative, you will find something different. So up to the kth derivative at 0, you will find that the value, will go to 1. So if it goes to negative 1, right, because that'll be negative 1, and then times some value of x, to the kth over k factorial. So the k derivative over here minus that value, of n will just be equal to 0, right? And then that value to the power of 0 is going to be 1. So we're left with the same, function. So that tells us that the Maclaurin series representation for a polynomial is just the polynomial itself. So you could just write that out. So the Maclaurin series representation for a polynomial, right, is just the polynomial itself. Is the polynomial itself. So that means that the answer is just going to be, f of x equals to x minus x to the k divided by k factorial. All right, so that's it for now. I wish you the best of luck on the exam tomorrow. Remember to double check your answers because you're always prone to making mistakes. So just do a lot of practice. Go home, do some problems from the back of the textbook, and good luck. So thanks for watching, and I'll see you next time. Also, remember to fill out this survey. It will be a great help for my project. So go ahead and go to this link. It's a short survey on student performance. So that's it for now. I'll see you next time.